So I stood up a little bit too early, a little nervous about this talk, as you can tell, but here I am. Thank you for the introduction. Do I have a clicker here? Green is forward, I assume. So, as he mentioned, my talk is automotive camera trends and how they're driving changes in optical designs. I wanted to give a very high-level talk on what we've seen changing in the camera specs from you guys, the tier ones out there, in the last years, and what we see in the future going forward as people start talking about ADAS with more functions, multifunctional cameras, autonomous vehicles, and how this all flows down to a subcomponent level. So there's two big trends we see, and I want to focus on the first one here. The first one being ADAS. ADAS used to be maybe just some very basic driver assistance functions like automatic like brake warning system that says maybe you should slow down. Now ADAS has grown and expanded to include many, many different functions, and people are trying to do as many of these functions with as few sensors as possible. You have functions like lane departure warning, headlight detection, oncoming traffic, automatic braking, maybe even automatic steering to avoid obstacles. You're trying to detect pedestrians, trying to detect cyclists, and you're trying to do all this detection with as few sensors as possible, which means maybe you're trying to do all this stuff with a camera, potentially. That drives some very interesting requirements for the camera spec and flows down to very interesting requirements for the lens specs, and it's pushing the state of the art. Another trend, of course, is that cameras in cars are now quite a big deal. It used to be that they were, we have one camera on a car. Now it's 8, 10. So there's, of course, pressure as you have more and more cameras out there to do some cost engineering, figure out, okay, we're making millions of these. How do we make it the most efficiently? How do we do more with less? How do we keep the same performance but make it at a lower cost? And these are both problems that Sonex has been finding solutions to over the last few years. So I'm going to just try and give a very broad overview of what's been changing. Some of you guys already know this. Some of you guys maybe are peripherally related to the problem. You write software or something. And I want to just make sure that everyone in this camera space is aware of how all these changes filter down to a hardware level. So in the past, you had cameras designed which were maybe just using a VGA sensor, less than 1 megapixel. They had big pixels, maybe 6 microns. You had a temperature range it had to operate over to perhaps -40 to 85 C. You didn't have the best dynamic range in some of the first generation sensors, maybe 60 or 90 dB. But now, looking forward, there's a lot of new exciting sensor technology out there, and we have to design cameras to accommodate it, lenses to accommodate the sensors. So now we're looking at 2 megapixels, 4 megapixels, 8 megapixels, and beyond. Maybe 10, 20 megapixels in the future for autonomous vehicles. Your pixel size is continuously shrinking. We're down to 3 microns, 2.8 microns. We could continue this trend all the way down to the 1.8, 1.6 microns you see for cell phones. There's been a bigger range of temperatures that people want to operate over, perhaps up to 105, 125 C. And there were a bunch of problems that people kind of knew about 5 years ago, ghosting, distortion, but nobody was quite sure how to spec at the time. And now everybody wants everything perfect and everybody wants it their way. And it's been driving a lot of innovation at the optics level. So I'm going to go over a couple slides for each of these different areas that technology has been improving in. This one I could probably give an entire presentation on, and in fact I've written a white paper on, so feel free to ask some questions later, maybe at the booth. But at a very top level, cameras used to be just designed to plus 85 C with the intent being survival, making sure that your coatings don't become damaged, your lenses don't crack, that you can put them on the car and you have confidence that the camera will still work in 15 years. And that problem was solvable, and it has been solved. But now, of course, as soon as you solve one problem, another one appears. That problem is that we want to operate over a wider temperature range. And we want to say not only does the camera survive, the camera thrives. You have a system where you want the performance to be the same, no matter if it's snowing outside or if you're in the desert. You want the image to look the same so that the algorithm sees the same thing, the algorithm predicts the same thing, and it gives a good result. So you have many different factors here. You have expansion of adhesives. You have changes in the optics. You have expansion of maybe some holder materials, some housing materials. You have the lens barrel itself is expanding and maybe the optics are shifting when it expands. And you have your PCB, maybe it's flexing or changing with temperature. All these things add up to a very complex system level problem. And it's not a problem that any one person in the ecosystem can solve on their own. And it requires a lot of collaboration between the optics provider, between the sensor guys, between the tier ones to identify all of the risk factors, how all these factors go together, and how to design a full system so that your optic balances with your housing, balances with your PCB, and that everything together results in a good image quality over the full temperature range. Of course, our pixels are getting smaller, so we've gone from 6 microns to 3, and very intuitively, if your pixel has shrunk in size by half, you can now resolve features that are twice as small. We basically, by going to these smaller pixels, have doubled our resolution requirements for the lenses. And in some cases, in fact, we see a move away from traditional RGB color sensors to something more like RCCC, RCCB, or monochrome. So you used to have these Bayer patterns where you could get away with some shenanigans from an optics standpoint. Your blue pixels were more separated than your green pixels, so were the red. So maybe if your blue and red performance wasn't quite as good, that was okay. That is no longer the case as we move to RCCC, as we move to monochrome. So another thing is that the ADAS cameras used to be, in the first generation, fairly basic, narrow field of view. They look forward. They do some basic detection on the car in front of you, and they have a limited range. Maybe they need to work 100 meters away. Now we see a push to do two different conflicting requirements. People want to see what's going on to the left and the right for cross traffic, for pedestrian avoidance, for cyclists, objects coming from the side. So you need to see a wider area. But simultaneously, there's also a push to detect the same things you were detecting before, and in fact detect them farther away. So you want to see the car in front of you, but maybe not at 100 meters, maybe at 200 meters, maybe at 400 meters. And this drives an interesting problem. If you just make a wide-angle lens to see what's going on to the left and right, you've reduced your magnification in the center, all other things being equal. So you have to do some tricky optical design, perhaps, to recover this. And what ends up happening is that you have some guy in a lab somewhere typing at a computer, writing an algorithm to run detection, and he says, well, I need at least this many pixels, maybe 10 pixels to be sure that I see something. And he writes that down on a spec sheet for the algorithm, and that flows to the tier one, it flows to me, and I look at it and I say, well, if I need that many pixels, I need a certain magnification. So what was originally an algorithm spec has become a lens spec. And sometimes the algorithm spec and drives a lens spec that's quite challenging. It's been an interesting move away from we say what the distortion is, and then the algorithm guy kind of deals with it 10 years ago, to the algorithm guy comes to me and says, look, we must have this to work, make the lens work, and we do. There's also other problems out there that people have seen over the years, of course, flare, ghosting, stray light effects. You have some directed flare of light, some focus ghost, some big blurry feature, veiling glare, or any sort of light that you don't want, an artifact caused by the imaging system, caused by a reflection from a housing material. All this stuff maybe it was permissible when you're working with human vision. When you have a human looking at the image, they can say, oh, that's just noise. I don't need to worry about that. But as you move to ADAS, as you move to autonomous driving, the algorithm doesn't know what's a real headlight and what's the ghost image of a headlight. It may cause a false detection. The algorithm can't say, oh, I should worry because there's this big bright spot. There might be something behind it that I can't see. The algorithm doesn't know that. So all these things that used to be objectionable but not mission critical are now mission critical. You have these strange big orange blurs that a human would look at and say, that's ugly. An algorithm looks at and says, what's going on? I have no idea. And then your car crashes. It's not a good solution, not a good problem to have, and it's one that we must solve, and in fact we have solved. So jumping back, what are the camera level trends? As I said, we have algorithms driving some optical specs, distortion, magnification. We have broader temperature ranges and more precise requirements for the temperature. You want to get good image quality over the full range. You have higher resolutions with smaller pixels, meaning you need a sharper camera system. You have these new pixel architectures also requiring potentially a sharper system. And you have, of course, dynamic range. These sensor guys have been very good to push up to 120, maybe now 140 dBs of dynamic range. But as these sensors get better, you start to, of course, see optical artifacts that you couldn't see before. And this has driven some innovation on our side. So I've just gone over what do the camera specs look like. Now, what do these specs look like at a lens level? If you write something on your spec at a camera level, what do I have to write on my spec at a lens level? Your pixels directly drive the sharpness, the MTF required. They drive what spatial frequencies we should be sampling at and testing at. Your distortion profile directly drives perhaps the design choices we have to make. What used to be maybe an all-spherical design now requires some aspheric components in order to get the magnification in the regions you want and not in the regions you don't. This greater stability requirement drives new material choices and greater modeling of the materials. Whereas previously maybe you just use all glass and it's stable and you say, okay, it's stable enough. Now you have to be very particular. You have to choose glasses that balance each other to compensate for focus changes over temperature. You have to be cognizant of not only your optical design, but also the customer housing, how these two interact. And you have to get better low light performance. And that means at some point, the sensor guys, they can add more and more dB, but you need more photons at some point. You must have the photons to work with to detect. And that means our optic needs a bigger aperture. We need potentially a lower F number. And we need also, as we let through all these more photons, we need to be even more careful that none of these photons are going astray, causing optical artifacts. So I tried to avoid too much math getting too in detail here, but here's a little bit of MTF charts for those of you who are familiar with them. Essentially, it's a measure of lens sharpness. You plot how good is your contrast for a given spatial frequency, a series of line pairs, say. And on the left, I have the graph for a first generation rear view system. It was designed around a 6 micron pixel VGA system. And what we were looking at the time, our spec was essentially the red line. The red line there had to be quite good, and that was what we were looking for. Now, the blue line at the time, which was performance at very high frequencies, nobody really cared because the sensor couldn't resolve that. On the right-hand side, we have a lens design sharpness plot for a next-gen lens. And you can see that now our blue line is where our red line used to be. We've essentially had to double the sharpness of the lens to deal with these pixel changes. So I mentioned before many of these optical artifacts that aren't acceptable. We've been working to slowly bug hunt these. It is a constant battle. You have, every time you correct a problem, you peel away the problem, you find the next problem underneath it, and the sensor sensitivity is constantly increasing and detecting these problems as well. So you have, say, a directed flare. We can detect that, we can eliminate that, perhaps with some better process control. You have some focused ghost. You can model the system, determine where in the system this ghost is from, what is focusing it. You can identify that surface and potentially change that surface to disperse that energy over a larger area, reduce the brightness, make it less likely to cause a false detection. And this is a design level change that has impact on the rest of the system. If you have to change a curvature to disperse some light, now that curvature is not quite optimal for sharpness. So you're making some trade-offs here to eliminate these factors along this process. You have these other factors, maybe they were caused actually by a reflection not in our optic, but in the housing behind the optic that we didn't originally know about, or maybe they're from some metal part in our system. We can work to model, once we have complete information on the rest of the system, what's going on, and then figure out, okay, well, we can baffle that, we can solve this problem. We can look at these sort of strange colored items and say, oh, well, that's actually from a particular coating. With some better coating process, some improvements to the homogeneity, we can eliminate this issue. And it's been a constant struggle. The interesting thing about these artifacts is that they are often very tenuous and hard to find. They are transient. So you take a camera, you scan it around, you'll see a defect or an artifact for just 1 second, and then it'll be gone. And in order to detect all these transient behaviors, you need to take a lot of images. So in your first article analysis, you need to take hundreds and hundreds of images in different scenes, in different scenarios, with lights at different positions in the image, with lights outside of the image, with lights shining from all different directions, to identify everything that's going on and optimize everything in the system. So, just jumping backwards, giving a broad overview. We have higher resolution requirements. We need to perform at higher spatial frequencies. We need lower F numbers, bigger apertures, more photons. We need to change the distortion profile, maybe use some different shapes, more sophisticated designs to match this. We need to make the design very thermally stable, not just as a single unit, but thermally stable when combined with the customer camera housing. And these requirements are not all going in the same direction. We're being pulled in many different directions to make everything perfect when everything affects everything else. You try and lower your F number, make a bigger aperture. That makes it harder to make the lens sharp. You try and tailor your distortion. That makes it harder to make the lens sharp. You try and make the lens very thermally stable. That drives you to particular material choices. It limits your options. And it's been a very interesting journey, this state-of-the-art progression, just trying to do more and more things with sort of a smaller and smaller solution set of ways to do these things all at the same time. And sometimes there are trade-offs. You might need to use more exotic materials. You might need to accept that in order to get a bigger aperture, your lens must be bigger. You might need to accept that whereas before you could get away with all spherical surfaces, now you need some aspheres. And it's been very interesting just to watch how ADAS requirements, algorithms, new sensors have driven optical technology forward over the last years. So with that, I've run through my presentation, perhaps a little quickly, but now any questions from the audience?
Thank the speaker and then let's have the first question.